It's so big. And I also realized there is not enough rocky material per unit volume in interstellar space to deliver such a giant rock into the inner solar system within a period of a decade. You would expect it at the very optimistic scenario where you package all the material into objects that are 5 kilometers in diameter. You would imagine once per 10,000 years. One way out of this dilemma of why is it so big is if it was targeting the inner solar system by design. And indeed, the trajectory is aligned with the plane of the planets around the sun to within 5 degrees. The chance for that at random is 1 in 500, okay? And it's moving in a retrograde trajectory opposite to the motion of the planets, which is ideal for it to release mini probes that will get into the planets. It gets close to Mars, it gets close to Jupiter, it goes on the opposite side of the sun relative to Earth when it's closest to the sun. And that's the time when a spacecraft could do a maneuver to take advantage of the sun's gravitational assist.
The discovery began quietly, with a Nordic astronomer performing routine observations under clear winter skies. He had no intention of finding anything unusual. His goal was simply to capture long exposure frames of 3I Atlas as it crossed a stable patch of sky. The air was cold and still, giving him excellent seeing conditions. When he stacked the first set of images, he noticed a faint circular outline surrounding the object. At first glance, it resembled the kind of broad halo that occasionally appears when a comet experiences minor outgassing. But as he processed the data more carefully, the outline sharpened. Instead of fading with distance from the core, the ring became more defined. This was the moment he realized the structure was not noise, it was geometry. A perfect ring, consistent in brightness and thickness, almost as if the object had pushed out material in an evenly distributed pulse. The astronomer then examined the raw FITS files to ensure no processing artifact was responsible. He checked each individual frame, each calibration step, and each pixel cluster. The ring was present before any enhancement. That eliminated software error. Within an hour, he contacted 2 observatories in Sweden and Finland. Both teams captured their own sets of exposures. Their images confirmed the feature with striking similarity. All 3 data sets recorded the ring at nearly the same radius, expanding at a uniform speed. That level of consistency is unusual for a natural body with uneven surface vents. The astronomer reported that the ghost shell behaved more like a pressure wave moving through a gas cloud rather than a chaotic dust burst. It did not wobble or fragment. It expanded cleanly, as if responding to a single moment of internal release. That is why this detection triggered global scientific attention. Symmetry and cometary activity is rare because natural surfaces are irregular. Most comets rotate unpredictably. Their crusts are fractured, uneven, and filled with volatile pockets that erupt in different directions at different intensities. For a ring to appear evenly around the entire body, the release must be uniform. That means every part of the surface would need to act in synchrony, something we do not see in typical outbursts. When a comet warms, sublimation increases. Gas streams escape through vents, cracks, and exposed pockets. These jets form lopsided shapes, not circles. The brightness of a natural halo varies with the orientation of the surface. Yet the Nordic ring did not show variations. It displayed near perfect balance along its entire perimeter, suggesting that the source of the expansion was not tied to surface irregularities, but to something deeper within the interior. Some models propose that internal pressure can accumulate in a subsurface layer. If that layer is consistent in temperature and composition, it might release energy in a smoother pulse. But most interstellar fragments are not expected to preserve such layers. Their journeys through radiation and collisions should break any uniform structure. Another explanation is a sudden phase transition that occurs when material inside the object changes state. This could generate a spherical shock wave pushing outward. But even in those cases, the ring tends to distort as the comet rotates, or as external forces interact with the expanding gas. What makes 3I Atlas more unusual is the stability of the ring. Its shape held for a measurable duration. It did not collapse, scatter, or fragment quickly. It expanded like a coherent front. That stability forces astronomers to question whether a simple, natural process is sufficient to explain it. If not, something more organized may be operating inside the object. While the ghost shell expanded outward, data from the Nordic observatory revealed a second anomaly forming behind 3I Atlas. A faint but well-defined line of bright material extended toward the Sun instead of away from it. This is known as an anti-tail, a rare optical effect that appears when heavier dust settles into the orbital plane. From Earth's perspective, it looks like the comet is growing a tail in the wrong direction. For an anti-tail to appear, 3 conditions must be met. First, the comet must release heavier particles capable of resisting solar radiation pressure. Second, those particles must settle into the orbital plane. Third, Earth must view the comet from the correct angle to see the inverted feature. These events do not align often, and they almost never occur at the exact moment a ghost shell forms. The challenge is that 3I Atlas does not produce large amounts of dust. Spectral studies show unusually low dust content compared to typical comets. Most of its emissions appear to be gas and ionized particles rather than solids, capable of forming a dense anti-tail. Yet the Nordic telescope recorded a thin, bright line that remained stable across multiple exposures. The brightness profile suggests the dust particles were large and released in a narrow velocity range. If they had been ejected randomly, the line would have spread into a broad fan. Instead, it remained concentrated. This implies a controlled release rather than chaotic venting. The timing also matters. The anti-tail began forming shortly after the ghost shell appeared. This synchrony hints that both phenomena originated from the same internal event. Astronomers now face a puzzle. How did a low-dust object produce a feature requiring heavy particles? And why did it appear at the precise moment a symmetrical ring expanded outward? The simultaneity of the ghost shell and anti-tail is the strongest argument that a single internal event triggered both. In normal comet behavior, different features arise from unrelated processes. Gas releases often precede dust expansions. Jet activity is sporadic. Thermal changes occur in patches. But here, 2 structured formations appeared almost back to back. To understand the significance, astronomers simulated various scenarios. In one model, a sudden internal fracture caused by thermal stress could release a uniform pulse of gas while dislodging heavier particles from a deeper layer. In theory, this could produce both a ring and an anti-tail. But for that to work, the interior must be stratified in a way comets rarely are. Another model looked at rotational pressure. If the object reached a critical spin rate, sections of its interior could shift or collapse, releasing material in a symmetrical burst. Yet the observed rotation period of 3I Atlas does not match the speeds required to produce that level of structural stress. A more complex model involves subsurface pockets of volatile ices arranged in a stable layer. If sunlight penetrated near the rotation axis at precisely the right moment, the entire layer could vaporize uniformly. This might create a smooth shockwave and a secondary release of dust. But again, this requires a level of internal order unusual for an object traveling through interstellar space for millions of years. The synchronized timing suggests coordination, not random chance. The ghost shell's perfect geometry and the anti-tail's narrow formation are consistent with an organized internal release sequence. Whether this is natural or something beyond standard comet, physics remains open to interpretation. What is clear is that the object behaved as if responding to a single command. Nordic observatories have a long history of capturing faint structures that larger telescopes often miss. Their advantage lies not in mirror size but in environmental stability. Cold air reduces atmospheric turbulence. Dry winter nights eliminate water vapor interference. Long periods of darkness increase exposure time without thermal distortion. These conditions allowed the Nordic observer to detect features around 3I Atlas that would be nearly invisible elsewhere. The telescope used was a high-precision 12-inch reflector with narrowband filters tuned to detect faint gaseous emissions. These filters isolate specific wavelengths associated with carbon, nitrogen, and oxygen ions. When applied to long exposures, they can reveal structures hidden within the broad light of the coma. When the astronomer processed the data, the ghost shell ring appeared strongest in these ion filters. That indicates the ring was composed mostly of gas rather than dust. Gas behaves differently from dust. It expands smoothly because each particle interacts similarly with solar radiation. This would normally create a diffuse halo, but in this case, the expansion formed a perfect outline. The Nordic team also compared their results against reference images of known comets with shell structures. Comets like Hale-Bopp and Holmes produced shells during major outbursts, but those shells were uneven. They showed distortions caused by rotation, vent asymmetry, and surface irregularities. The ring around 3I Atlas lacked those distortions. This is what made the Nordic detection so significant. The environment, the equipment, and the filtering all contributed to revealing a feature that could easily have gone unnoticed. The telescope did not simply capture a halo. It captured a fingerprint of internal behavior, and that fingerprint is remarkably clean. When a comet undergoes an outburst, astronomers look for several hallmark signatures. First is a rapid increase in brightness as gas and dust escape. Second is asymmetry in the expanding material. Third is a rise in surface temperature as deeper layers are exposed. Fourth is a chaotic coma that thickens unevenly around the nucleus. 3I Atlas did not follow any of these patterns. Its brightness increased only slightly. The ghost shell remained symmetric, infrared data showed no temperature spike, and the coma stayed thin despite the expanding ring. These deviations matter because they separate typical outburst behavior from unusual internal events. A natural cometary outburst is messy. Material explodes outward in clumps. Jets produce inconsistent shapes. Temperature gradients emerge across the surface. Even comets with smooth layers cannot produce the level of uniformity seen here. The closest analogue in modern observation is the 2007 outburst of Comet Holmes. That event produced a vast spherical shell that shocked astronomers with its size. But Holmes released enormous amounts of dust. Its brightness surged dramatically, and its shell, though spherical, still contained irregularities caused by rotation and turbulence. 3I Atlas behaves differently. It has low dust content, its brightness changes are modest, and its shell does not show rotational distortion. This suggests the mechanism behind the event is not surface venting, but an internal process with consistent pressure distribution. Some researchers propose that the interior of 3I Atlas may contain layers of volatile materials preserved unusually well. Others argue that the symmetry implies a rigid or semi-rigid internal structure capable of transmitting pressure uniformly. Either way, the object does not fit comfortably within the catalogue of known comet outburst behavior. It is acting like something more organized,